Again, welcome everyone. This class is CS 11747, Neural Networks for NLP. If you're in the wrong room, then now you know, so you can leave and I won't get mad at you. The first thing that I want to talk about in this class is intro and also why neural networks for NLP. And I will be talking about a little bit about the class format and a little bit about intuitions and a little bit about kind of just getting started stuff. I think a lot of people in this class might not know or might know a lot about neural networks already. You might have already used them in your work. I think a few people in this class might have not used them very much. Because I think a lot of people know at least a little bit, I move relatively quickly through the intro stuff, but I try to give resources for people who don't know quite as much. So if you're somebody who falls in the latter category, make sure you read the resources carefully, come to TA office hours frequently, and try to catch up to speed. So, the whole motivation behind this class and the reason why we're interested in natural language processing or other things in the first place is that language is hard. And to give a simple example of this, I want to talk about grammaticality tests or naturalness tests of language. These are standard things we use in linguistics to describe a language. We say, is this sentence natural in this language or is it not natural in this language? Are these sentences natural English? If you think the answer is yes, raise your hand. Okay, good. If you fail this, then I think you'd have trouble following along with what I'm going to be saying for the entire class. But, so Jane went to the store, of course, yes. This is natural English. It's a very stereotypical English sentence. Actually, I'm sorry, if you're sitting down and there's a hole in the middle, would you mind moving in so people in the aisles can sit? Thanks. So then the next one, what about this sentence? Who thinks this is natural English? Nobody, okay, good. We've gotten this far. So what about this one? Is this natural English? Maybe not. It would be natural in some other language, maybe, if you didn't have the or you didn't have determiners. So, for example, I know this is natural in a lot of languages, like maybe Russian or Japanese or other languages that don't necessarily use determiners. Okay, what about this one? Who thinks yes? No? Well, my 2-year-old daughter might think this is pretty reasonable English, but it actually isn't. And the reason why is obviously it's an overgeneralization. You think you know the words decided, explored, other things like this, so you figure that you can add D to the end of the word and get a past tense, but in fact it's went. It's an irregular verb. What about this one? Who thinks it's okay? Okay, I see a few people raising their hands. I think the reason why is because this is syntactically okay. It's fine, right? It's fine English syntax. But in reality, stores aren't things that go places. So semantically, this is a little bit strange. Yeah?
It could mean an inheritance.
Yeah, okay, so that's true. So if you took went as in not the meaning of like physically to go, but instead inherit something, then that's completely correct. So you're the first person who pointed this out in 3 years or in four iterations of this class, but that's a very good point. And okay, so what about this one? Is this natural or something that you can see happening? Okay, sure. But you could also say a food truck is a subclass of a store, right? It's a place where you sell things. So you can't say that, you know, all stores or all shops will never go to somebody, but in most cases they won't, but in some cases they will. So as I said, language is hard. There's lots of rules, there's lots of exceptions to the rules, and we need to consider all of them. And in order to do this in NLP systems, we very often come up with engineering solutions. And now let's say we didn't know anything about neural networks at all, or maybe we didn't know very much about machine learning. What we could do is we could create a grammar of the language that specifies all the grammatical rules. It also specifies the morphology. So like how do you turn verbs into past tense verbs, for example? Also the exceptions, so you know that go is an irregular verb, so it cannot turn into goad. You could also come up with semantic categories, like things that tend to go places. And things that tend to go places might go together with the verb go, but they also have exceptions. So the difficulty here is, up until maybe the 1990s, when kind of the revolution of machine learning took over natural language processing, this is very much what people tried to do, and this doesn't scale well. There's lots of exceptions. And then, of course, if I ask you to do the same thing for these sentences, who in here would be able to do that? I see 4 people, which is very good. That's much better than my machine translation class where we had 0. But this is in Japanese, so obviously you would need to be able to know Japanese to do the same thing here. And if you start getting down to languages where you have fewer speakers, it becomes much more difficult. So just to summarize, the phenomena we need to handle in order to process natural language to make these sort of grammaticality or naturalness judgments are things like morphology, syntax, semantics, and world knowledge. If you're talking about a big like dialogue or document, you need to also consider discourse. Also pragmatics, which is like in what situation or like, is the language use appropriate based on the situation? What is the meaning based on the situation? And of course, also multilingual processing. So neural nets are very interesting, I think. They're interesting from a machine learning point of view. If you're someone who's interested in studying the inherent properties of learning these things. I'm more of a practitioner. I want to do things, but the reason why I'm attracted to neural nets is because they are a tool that allows you to do very hard things, and it allows you to be very flexible in designing models that handle all of the phenomena that I talked about in the previous slide. So the main point of this class, or the main goal of this class, is to give you the tools to handle the problems that you want to solve in NLP with neural nets, and also, potentially improve on neural nets themselves, although that's not the main, on existing methods for neural nets themselves, although that's not the main goal of this course. So are there any questions so far? I think this might have been kind of basic intro stuff. Okay. So I'll go into the class format and structure very briefly. This is important to understand so you know what you're getting into. The class format, before the class, for each class I have reading material. I try to make the reading material anywhere between 6 to 10 pages. And the idea of this is to get the basics of what I'm going to talk about in the class. Very often it will be reading materials about non-neural network linguistic information that you need to know as background. If you've already taken linguistics classes or NLP, non-neural NLP classes, I think a lot of it might be, you might know it pretty well already, but it should be a good refresher. Then during class, at the beginning of class, we have simple questions about the required reading. This is just to provide motivation to ensure that you do the reading before the class, so we can go in and discuss advanced topics during the class based on the idea that you will have known the reading. And then I will give a brief summary of the material that was in the reading, just because I feel this is a good way to get people to ask questions that they didn't know about or things like this. Then we'll have elaboration where we will field questions and elaborate on details and talk about advanced topics. So this is where we really get into the new interesting stuff that's been going on in this area. Also, for some subset of the classes, we'll have a quick code walk. The idea of this is just to give a basic idea of like how you would actually implement something like what I talked about in class. It's usually one example from all of the things that I talked about during a single class. And this will be all of the code in the code walks is available in a GitHub repository, which I believe is also linked on the site. If it isn't, then I'll link it here. But it's this Neubig, my last name, /NN for NLP code. And you can go here and take a look at the code examples as well. But I'll just, the idea of the code walk is to walk through this briefly so you know what to look at when you go back and look at it yourself after the class, for example. Then after class, you can go in and review the code. You can try to run and modify it yourself, visit the office hours to talk about questions, etc. And at the moment, the code examples from the previous classes are mainly written in Dynet, which is a neural network library that I wrote. But starting this year, one of the TAs who I'll introduce in a second has agreed to also translate them into PyTorch. So we'll have a parallel corpus of Dynet and PyTorch that you can use to study either one of them or study both of them at the same time if you want. So the scope of what I'm going to be talking about this time is basics of general neural network knowledge. As I said before, this will only be covered very briefly. So if you're not quite familiar with basics of how to implement neural networks, I suggest doing the reading early, trying out the code examples, and talking with the TAs a lot. Advanced training techniques for neural networks, there will be some coverage. Like we'll talk about variational autoencoders, adversarial training, mostly from the scope of NLP. It won't be as much as your deep learning class. So if you want to take a class on these kind of things, on deep learning, for example, deep reinforcement learning would be better choices of classes. What we will talk about in detail, more than the other classes here at CMU, will be advanced NLP-related neural network architectures, and also an introduction of NLP tasks that these have been used to tackle. I think this will be informative. Also, structured prediction and structured models in neural nets. So this is very, very important for NLP, maybe more so than for other tasks. So I'll be talking about structured prediction methods. And also, finally, implementation details salient to NLP. One of the goals of the class is that by the end of the class, everybody in the class should be able to implement a state-of-the-art NLP-based NLP-based neural network model. And in order to do this and get this to work, there's actually lots of tricks about how to make it fast, how to make it, debug when you're having trouble, how to interpret your results. So I'll also be covering stuff like this. In terms of assignments, the course will largely be group assignment based, which means you'll form groups of 2 to 3. The first assignment, however, this is a change from the previous year, will be individual. It will be implementing a simple text classifier in using neural networks and trying to get reasonable accuracy on a benchmark data set. And we haven't decided this yet. This will be due mid-February, or like early to mid-February. So there's still a little bit of time about how to do this. Then for assignment 2, basically what I want people to do is the final assignment will be a project. So for the second assignment, we're going to have people do a survey of the state of the art in the particular task that you want to handle. And this will just be, explain about the existing methods and what you think their advantages and disadvantages are and how you'd like to improve them. For the third assignment, this is maybe the hardest assignment of the entire class. What I'm going to ask you to do is to actually re-implement basically from scratch You can use a neural network toolkit, but you can't use existing code, a state-of-the-art model for one of the tasks that are using. So you take the paper that you had, you reproduce the results on the data set there. Then the final assignment will be a final project where you perform a unique project that either improves on the state-of-the-art or applies neural networks to a unique task related to the thing that you did in assignment 3. So this is the class, these are about the class format. Is there any questions about this? No? Okay. So in terms of the instructors, there are 2 instructors for the class. I'm the main instructor for the class, and I'll be teaching most of the classes here. In addition, Antonis Anastasopoulos, who will be a postdoc here, he's defending his PhD thesis in 6 days, so he isn't quite finished yet, but he'll be here. He'll also be covering some subset of the classes. We also have 6 wonderful TAs, if you guys don't mind standing up so people know who you are. So these are the TAs. I will introduce them not in the order that I have on the slide, but rather in the order that they are here. So this is Dan how do you pronounce your last name? Clotho, okay. So Dan Clotho. So Dan is currently working on OCR, optical character recognition, but he has also done work on parsing and other things like this, so he'd be a good person to ask if you want to know about OCR or parsing. Danish is he's worked on a number of things, including training word embeddings and other things like this, but right now he's most interested in interpreting neural networks for NLP. So he's a good person to talk to if you want to know about how to interpret the models, and he'll also be teaching a class about that. So Trunting has done a lot of things. I think the general theme of the research is, in general, like advanced machine learning models for NLP, but specifically generative models, like variational autoencoders or other things like this. So she's a good person to talk to if you want somebody to go through the derivations of a difficult paper, or like generative models or things like that. Actually, kind of a similar thing goes for Junchan, like general machine learning for neural networks for NLP, but specifically generative models as well. And they're both going to co-teach a class on generative models for NLP. You guys, I don't actually work with you, so maybe it'd be better if you introduce your research topics.
Yeah, so my research interest is mostly.
This is Vaibhav, thank you.
And it's mostly multimodal problems, and I've also worked on machine translation and bilingual lexical.
And I'm Jean-Baptiste, or JB, for short. And I've worked mostly on social media Twitter analysis, but I've done some work also in like multimodal stuff. There's like radio processing, computer vision, with NLP.
Cool. So yeah, actually, I don't think I mentioned it in the slides, but we have a list of suggested tasks. So if you don't know what task you want to handle for the course project, we have a list of tasks that you can take a look at and find interesting ones. One thing I realized is we don't have very good ones on social media analysis or stuff, so if you can tell us some suggestions later, we can add them to the list. But that's what we have for the TAs. So one important thing about this class is it's pretty self-directed. So we only have one assignment that's actually a concrete assignment, and then the remaining assignments you get to be creative. I think that's a good thing if you're a grad student looking to come up with things that are relevant to you and things that you're interested in. But it also does mean that if you're not quite as familiar with neural networks for NLP, you'll have to do a little bit more work to make sure you follow along with the code examples, et cetera, and meet with the TAs. And we will have 8 office hours a week because we have 8 people teaching the class, which means there's lots of different times that you can come in to like ask about things. As a pro tip, my office hours tend to be much more crowded than the TA office hours. So if you want to talk about implementation things, the TA office hours might be more open, but I'm always happy to talk to people as well. Okay, so that's all the things for the class. Oh, wait list. So the wait list right now is like 50 people or something like this. In my experience, a lot of people drop in the first few weeks of the class here at CMU because you have multiple options and you decide which one you like. So I think if you're on the wait list, there's still a pretty good chance that you'll get into the class, but of course we can't guarantee it. So if you're on the wait list, you can continue to come until you get in or give up, I guess. Are there any other logistics questions? Yeah.
Auditing in class.
What's that?
Auditing in class.
Auditing. Okay, so the audit condition for the class. I mean, I prefer you take the class if you can, but if you audit the class, the condition for auditing is you need to get more than 60% on the quizzes in class. There's no project. If you're auditing, we will not grade your project also. So, yeah. Any other questions? Yeah.
Any exams?
There is no exams, other than the in-class quizzes. Yeah. Anything else? Okay, great. Also, we have a Piazza, which you can find on the class website. That's a really good place to ask other questions if you think about them later. Okay, so now to move on to a little bit of technical introduction. To give an example of a task that we're interested in, sentence classification, we can think of a very simple sentence classification task, which is sentiment classification. So if we have I hate this movie and I love this movie, the task is splitting this up into 5 classes where the sentiment is very good, good, neutral, bad, very bad. So this is maybe the easiest question that you'll have the entire time. What is I hate this movie? Very bad, okay. And I love this movie. Very good. Okay, great. So is one way to do this. I think probably most people know this already, but it's interesting to write this in the same notation as you write, or same format as you write a neural network. But let's say we wanted to handle this with a bag of words model. So a bag of words model is something that takes all of the words in the input and adds together scores for all of them. So basically what we do is we look up each word, and for each word we have a score. For the top score here, the top score here is the score for very good. This is the score for good. This is the score for neutral. This is the score for bad, and this is the score for very bad. And we also have a bias. This bias tells us basically how likely is this a priori for very good, good, bad, neutral, bad, very bad. We add all of these scores together. We take the score, and maybe we take the highest score and output that is the class for this sentence. Also, if we want a probabilistic classifier, we can do something like take these scores and run them through a softmax function where run this through a softmax function where the softmax function basically takes the score for a particular class and normalizes it by exponentiating it and then dividing by the sum of the exponentiated scores and turns it into a probability. So these are very simple models. You wouldn't necessarily call them a neural network, but this is one example of a way you can solve this. And in this case, if you think about what each of the vectors represents, each word has its own 5 elements corresponding to very good, good, neutral, bad, very bad. And obviously, hate will have a high value for very bad, love will have a high value for very good, etc. So how many people have been to the 8th floor in the machine learning department and seen the bag of words there? Oh, actually not that many people. So on the 8th floor of Gates, there's a art installation called The Bag of Words, where it's a bag full of words. And I think one of the reasons why it's representative of the machine learning department and not the language technologies institute where I am is it's not really thinking about language that much. You're just throwing a bunch of words into a bag and classifying based on that. But it's actually it's a pretty decent baseline. And the reason why is because love is very indicative of something being good. Hate is very indicative of something being bad. So you can actually do pretty well with even just that simple baseline with sufficiently sophisticated machine learning. However, you can also easily come up with examples that break this bag of words model, right? So I don't love this movie. What would this be? Bad, very bad. Yeah, people are kind of on the fence about this, but I'd say maybe bad. It's not horrible, but it's not good either. But then you also have there's nothing I don't love about this movie, which is very good. Or I'd almost if you could go from 1 to 10, I'd put this 11 maybe. So the thing here, though, is words like don't and words like nothing aren't necessarily very indicative on their own, right? You could have the word don't in a negative review. You could have the word don't in a positive review. So they only really become indicative when you combine them together with stuff like love. So don't love is a bad thing, right? And then nothing I don't love is a good thing. So this reveals a necessity for basically combining together different features to make decisions about things. So for example, does it contain don't and love? Does it contain don't and I and love and nothing? Would be examples. So the basic idea of neural networks for NLP prediction tasks is these are a way to take in elementary features or elemental features like what word exists in the sentence and combine them together and come up with combinations of these elemental features that are informative for the downstream task. So what it looks like is we look up a whole bunch of features here. We throw them into some complicated function to extract combination features that we then use to calculate our scores directly. And this is every single model that I'm going to be talking about in this class is based on this. So now we can all go home because I've taught you what you need to know. No, but the thing is the details are in how we create this function and also how we learn the parameters of this function in an appropriate way to solve our tasks. Yeah, and of course we can calculate probabilities. So to give one example of a concrete instantiation of this big kind of black box feature combination tool, we have the continuous bag of words. So the continuous bag of words is sorry, I'm actually missing a citation, but I think it's the only reference that's on the webpage for today. It's by Iyer et al., I think 2015, called Deep Unordered Composition Rivals Other Methods for Composition in Text Classification or something like that. And basically what the model is, that's the next slide. So this slide is something simpler than that. But the continuous bag of words, basically what you do is instead of looking up the feature scores directly, instead of looking up the scores for each output directly, you instead look up features for each word, and you add up all of these features, and then you multiply this by a weight matrix that turns these features into scores. So maybe these features will be 100 different features for each word. Then you multiply this by a 5 by 100 weight matrix, which turns the 100 value feature vector into 5 values that you then add together with your bias and use to calculate your scores. So the idea here is now that so if you think about what your vectors represent here, each vector has features. It could be, is this an animate object? Is this a positive word? Is this a negation, etc.? And we sum the features and then use them to make predictions. So, for example, if all positive words got grouped together with these features, then maybe that would be informative. The thing to note here, though, is we still don't have any combination features. This is still a linear combination. So only it only has the expressive power of a linear model. But you can do things like reduce the dimensions. If you create a very small feature vector, you can explode the dimensions and make bigger features as well. But this is not really the really interesting model. The really interesting model is the next model. So to get into the actual interesting model, which is the model from the paper that I mentioned a few slides ago, this is the deep continuous bag of words model. And basically what this looks like is you do the same thing as the continuous bag of words. And what this does is this adds up all of the features in a sentence, gets a feature vector, but then instead of using the feature vector as is to make the prediction, what you do is you run this through a couple layers of nonlinear functions. And what the nonlinear functions do is basically the layers of multiplying by weight matrices and doing nonlinear functions. Basically what this allows you to do is this allows you to extract combination features, like does a negation and a positive word appear in the sentence? Then based on these multiple layers of features, you can then multiply it by a weight matrix, add a bias, and get your scores, and use this to make your predictions. So in this case, our vectors represent things that are more interesting. A node in the second layer might be feature 1 and feature 5 are active. So as I said, if feature 1 is a negation, feature 5 is a positive word, then you can express this. And I'll be talking about this in a little bit more detail next time. So to make things a little bit, are there any questions about this so far? I'll be talking in detail next. Is that okay? Okay. So what exactly do we mean by when we say like a neural network? So a neural network, the original motivation of a neural network, as I think many people have heard, is neurons in the brain. And this is an illustration from Wikipedia of what a neuron looks like. Obviously, I don't think our actual neurons look quite this cartoonish, but the basic idea is the neurons in our brain, they have a bunch of, essentially on the left side, you have a bunch of inputs where they take electric signals and then they go through, and if the neurons reach a certain level of activation, they have an output. So I'm not a neuroscientist, so I'm not very qualified to talk about this in detail. I'm sure some people in this room are more qualified than I am. But the idea behind neural networks is you have a bunch of features, you run them through weights, you add them together, and you get a certain level of activation. And then if you exceed that level of activation, the kind of node, the next feature turns on. So basically, this is motivated by a similar thing here. However, even though this original motivation was based on neurons in the brain, now what we talk about when we talk about neural networks actually doesn't even need to remotely represent anything that we're doing in the brain. There are some people who are still very interested in doing things like this. For example, Jeff Hinton, who was one of the godfathers of neural networks, still is very interested in kind of neurologically motivated things. But the current conception that we use in most of our engineering-oriented or application-oriented research is simply a graph of differentiable or sub-differentiable calculations that combine together, smaller calculations into a string of smaller calculations into a bigger string of calculations. So the current conception of neural networks is much broader, I guess, than the original conception. So just to give a single concrete example, what we want to do is we want to calculate an expression. We want to calculate a mathematical function. And let's say, for example, our expression is x. We can create something called a computation graph that basically expresses this function. And in the case of x, this is a single variable. So we have this single node in the graph. And this node can be it can be a single scalar value. It can be a single, floating point value. Or it can be a vector of values, like I was talking about before. It can be a matrix, so two-dimensional. Or it can be a tensor of arbitrary dimensions. So it could even be, I have 3, 4, or 5 dimensions, etc. So any node in the graph kind of represents a value. And now let's say we want to modify this expression and get x transpose. Let's say x is a vector. So we have another node where this node represents two things. One is that it represents a function application. The node represents a function application. So a node with an incoming edge is a function of some arguments. And each edge is a single argument to the function. So transpose is a unary function. So it has a single incoming argument. So in this case, its argument is x. And this node represents transpose. And the node transpose, in this case, has to be able to calculate its function. So the function going forward to calculate the actual value, and the derivative of that function with respect to each of its incoming arguments. So in this case, I'm showing the example of transpose. I mean, the details of transpose are not very important. Just the fact that you are able to calculate these two things is the important thing. So then functions can be nullary, unary, binary, n-ary. You can take as many inputs as you want as long as it satisfies the fact that you can calculate the function itself and the derivatives of the function with respect to each of the arguments. So another example would be a matrix multiplication. So now we have x transpose times A, where x is a node. Then you have x transpose calculated from x. You have A, which is a matrix. And then you have a matrix multiply, which is a binary function that takes in these two arguments. Computation graphs are basically directed and acyclic graphs where you have unary, binary, trinary, or n-ary functions, and each of these functions can calculate forward to calculate its value, and backwards to calculate its derivative. So this is an example of a kind of complicated function. It's a polynomial function where you have matrix A, a vector B, and a scalar C, which are all kind of maybe parameters, and then X, which is an input to the function. And you can see that there's various nodes in here calculating various functions, and in the end, we get this rather complicated expression. So the final element of a graph is basically assigning a name to a node. So if you want to create basically create a function like y equals x transpose a x plus b times x plus c, in this case, the intermediate arguments don't have any names. We don't have any assignment. But the moment we add an assignment to y, we now label the node that y corresponds to with its variable name. So basically, a variable is a labeled node within the graph. So you can see there's kind of a connection between any mathematical function that we want to calculate in these graphs. And so the nice thing is, we can take functions that are written in a paper and directly map them onto something we can calculate in a graph, with the one caveat that all component arguments of the function must be forward calculable and backward differentiable. As kind of a corollary to this, if you're using a neural network toolkit like PyTorch or DyNet or TensorFlow or something like this, it also ideally should be something that's implemented within that toolkit as well. So, that's a practical concern. So within these models, there's a number of algorithms that you need to be aware of. Graph construction. So you construct the graph corresponding to the function that you want to calculate. There's then forward propagation. Forward propagation means in topological order, you compute the value of the node given its inputs. So forward propagation, basically you start out with all the values that you already know, like your inputs and your parameters, and then you gradually step through the graph to calculate the values from the bottom to the top, or in this case, in topological order. So this is done within a neural network toolkit that you would be using. This is not something you generally have to implement yourself unless you want to implement things from scratch. For back propagation, again, this is similar. What you do is instead of forward topological order, you process examples in reverse topological order and calculate the derivatives of the in the end, what you finally want to do is you want to calculate the derivatives of the parameters with respect to the final value. The final value that you calculate the derivatives with respect to is usually a loss function. So a loss function is a value, essentially it's a value that you want to decrease. It's a value that you want to be lower if your model is working low. And usually it's something like the negative log likelihood. I'll talk more about this later, but it can be any arbitrary function that you want to minimize. Then finally, we do a parameter update, which moves the parameters. It says in the direction of this derivative, but actually in the opposite direction of this derivative. One simple way to do this is using an update stochastic gradient descent, where you basically add in this derivative with a set learning rate alpha. But there's also lots of other algorithms that you can use to do this, which I'll also talk about in later classes. Are there any questions so far? As I said, I think a lot of this will be introductory for some people, but hopefully, it gives an intro to the stuff that I'll be talking later and gives the terminology. So there's lots of neural network frameworks out there nowadays, and in fact, probably the popularity of deep learning now is largely due to the fact that you don't need to implement these neural network algorithms yourselves. Most of them are already implemented for you. I remember that when I was taking my machine learning class, this was not the case. I remember even 3 years ago when we started writing DyNet, this was largely not the case. There were only a few neural network frameworks out there. But now there's a bunch of really, really good neural network frameworks that do everything for you. One of the first major ones was Theano. It's now been discontinued. There's also been Caffe, which now has been upgraded to Caffe 2. This is largely used for computer vision tasks. Following that, shortly after, was DyNet, the neural network toolkit I've been talking about a little bit that we developed. At about the same time, there was a toolkit called Chainer. There's also been MXNet, which was developed by here at CMU and then taken over by Amazon. TensorFlow, which has been developed by Google. PyTorch, which is a continuation of Torch, which was kind of a more general purpose auto differentiation library, but also developed largely by Facebook. Sorry, I gave away my quiz. My quiz was what's the difference between the ones on the left and the right? But since I already gave away my quiz, I'll just say it. The ones on the left are ones that are largely based on static declaration of computation graphs. And the ones on the right are ones that are largely based on dynamic declaration of computation graphs. And specifically for NLP, I recommend that you use one of the ones on the right. By default, I would suggest that you use PyTorch. But for some particular applications, I think DyNet is a better choice, specifically ones where you're doing things with complicated structures and stuff. So we can talk more about that later, and we'll have implementation examples for both. Um, Also, some of the ones on the left have kind of started moving to the right. Like there's TensorFlow MXNet Gluon and TensorFlow Eager. Um, so I think people are starting to, like all of the frameworks are starting to move in the direction of allowing dynamic declaration. But um, just to give an overview, the basic process of training in a dynamic neural network framework is you create a model, you declare its parameters, et cetera. And then for each example, you create a computation graph that represents the computation that you want. You calculate the result of that computation. And then if you're training, you perform backpropagation and parameter update. So this is a contrast to something like a static framework, like TensorFlow in the kind of non-eager mode, which is in this case you create the graph before you even start training the model whatsoever. There's advantages and disadvantages of static versus dynamic frameworks. The advantage of a dynamic framework is this gives you lots of flexibility. So let's say you had a different graph for every sentence that you wanted to process, or every instance that you wanted to process. The fact that you're recreating the graph every time you process a training example means that it makes it very easy to do this. However, creating a graph has a fixed amount of overhead. It takes a certain amount of computation time. So if you can do the same thing easily in a static framework versus a dynamic framework, you are very likely to see the static framework will be a little bit faster. And there's also advantages for like deploying models to other devices and stuff like that. So it's kind of a trade-off that you should be aware of. And for this particular class, we don't specify that you should use a particular framework, but we will give you examples in PyTorch and Dynet. So those are the two that I would suggest the most. Are there any questions about this so far? No? Okay. So I only have about 10 more minutes. So, or no. Oh, I have 30 more minutes. Okay, good. So I won't have to rush too much. Probably won't use all the time. But so I'd like to give a few concrete examples based on the examples that I showed before. So for example, in the bag of words, we have a code example of how you would code this up. So note that this is not a neural network as we normally think of neural networks. Normally neural networks are defined by the fact that we're using complicated kind of compositions of multiple functions, whereas a bag of words is really, really simple, right? You're just adding up scores. And you can use any number of other alternative training methods for them. But because the bag of words is still a function of lots of different operators, like adding things together, taking a softmax, et cetera, it is trivial to implement in any neural network framework that you're interested in using. So I have an example here of how you would implement this. And of course, you have the requisite imports at first. Then the next thing that you do is you read in your training corpus. Oh, so sorry, I forgot to show an example of the data. So the data that we have for the code examples basically looks like this. And it's exactly the text classification data set that I talked about before. It's a sentiment analysis data set where you have, it's from the Stanford Sentiment Tree Bank, and basically you have 5 classes. There's 0 index, so class number 4 is the best class. Class number 0 is the worst class. And then we have the rock is destined to be the 21st century's new Conan, and that he's going to make a splash even greater than Arnold Schwarzenegger, Jean-Claude Van Damme, or Steven Seagal. This is great, rated as good. It seems kind of very good to me, but I guess you could make an argument that it's good. And then if you go to a bad one, it says, a sour little movie at its core, an exploration of the emptiness that underlay the relentless gaiety of the 1920s. The film's ending has a "what was it all for?" So, yeah, it's pretty brutal. Interesting. Sorry, this is a complete. This is completely unrelated to neural networks, but an interesting fun fact about this data set is actually Seagal from Steven Seagal is one of the most strongly negative features in this data set. So Steven Seagal, I feel really sorry for him, according to Amazon reviews. But anyway, so we have this data set, so we want to read it in. And the first thing that you do when you read in a data set is neural networks like to work in vectors, like to work in space of vectors or something like this. So the first thing that you tend to do is you take all of the words as text and you convert them into integers. And the reason why you use integers is to look up vectors in a matrix. You need an integer ID to look up the vectors in a matrix. So the first example that we have here, this is kind of a little trick that allows you to convert words into word IDs. But you convert words into word IDs, you convert tags into integer tag IDs. You also have an unknown word, so you make sure that you have a word to handle all the words that don't appear in your training corpus. And then you read through and read in your data set to get a tuple of words and tags for each of the examples. So you read in the training data, you get the number of words that you have, you get the number of tags that you have. This is just to print out an example. Then we step into the actual part of training a neural network. So as I said, the first thing that you do when you train a neural network is you define a model. So the two cells here are defining a model. This is defining a trainer that basically implements something like SGD for you. It's implementing something called Atom that I think a lot of people know, but we'll talk about next time as well. And then we define parameters. So here within DINET, which is the example of the toolkit we're using here, we have parameters equal to the number of words in our training corpus times the number of tags. So if you remember, each word has a score for each of the tags. So this is simple, and this allows us to look up each vector for these. We also have a bias vector, and this bias vector basically will allow us to kind of capture the frequency of each of the tags. So then below here, we have a training loop. Maybe I'll skip to the training loop. So what we do in the training loop is we do a certain number of iterations over the corpus. In this case, we just do 100 iterations. We then randomly shuffle the training data. The reason why it's important to randomly shuffle the training data is because we want to make sure that the training data isn't ordered in a strange way. So for example, let's say if all of the negative tags were after all of the positive tags and we went through the training data in order, on the last iteration, we might get something that really likes negative examples because it saw all the negative examples last. So this is an important thing to do when you're using any variety of stochastic gradient descent. We calculate the training loss. We have some timing information. Then we call this calculate scores function for each of the words. And then we calculate a loss function. This is the negative log likelihood. I'll talk about this in detail next time. We add up the loss for the training data. And then this is calculating the forward pass through the data. So this gives us a training loss. We then calculate the backward pass because we're doing training. We perform an update. And then at the end of the iteration, we print out the loss in the time, and we try to see that this is decreasing. Then for testing time, we step through all of the words and the tags in the development set. We calculate the scores. We calculate the maximum value, and then we predict. We see whether our prediction is correct, and we calculate the test time accuracy here. So this is pretty simple. It's a pretty standard training loop. If you've written a neural network, it should look very familiar. And actually, we won't have to change this training loop no matter what model we use. So as I said, kind of a neural network is this big fuzzy function that converts all of our, all of our inputs into a continuous vector that we can then use to make predictions. So this function, calc scores here, is where all of our, like interesting architecture design goes into. So in this case, we don't have a very interesting architecture. We're just looking up scores and adding them together. So this is a specialized DINET function that creates a new computation graph for you. So we, as I said, we create a new computation graph for each example. So then we do a Python list comprehension that looks up a score for each of the words, and then we sum all of these together. We add the bias vector, and we return this as a score. So if you look at this, and then we go back to the PDF that I just showed you, you can see that this basically implements exactly this function. You have your list comprehension, which is looking up all of these. We have a bias function, which is, or a bias vector, which is creating this. We then have a sum over all of these values, and we create the scores. So the nice thing about neural networks is this very strong connection between these graphs that we can draw in our paper, between the equations that we write in our paper, and in the final code that we write. Normally I would run this, but I forgot to open my Jupyter notebook before class started. So you can go back and run it on your own if you want to. But are there any questions or elaborations about this as an implementation example here? No? Okay, so I will note that this is an extremely simple example, and there are more things that you need to think about in order to make things like efficient when you're using more complicated models. But we'll be talking about those next time and the following times as well. So then the question is, how do we use this to create a more interesting model? And the answer is that it's basically the same, with the exception that we will be using a different thing. We'll be declaring a slightly different model, and we'll be using a different thing for our calculate score function. So for a slightly different model, we kind of declare an embedding size to be equal to 64. And when we look up our word embeddings, we, instead of looking up the scores directly, we look up a word embedding of the size of the embedding 64 here, and then we output. So the implementation of this is here. We look up the continuous bag of words. We multiply it by a parameter matrix, and then add a parameter bias. And this is exactly the same. So with a minimal change of a couple lines of code, we now have a new model that we can test out and see if it works better. So then finally, let's say we want to go all the way to our deep model. Again, all we have to do is calculate the parameters in a different way. So now we have the final weight matrix here, defined as this. And then for each of the layers of the hidden dimension, we have a single weight matrix. Here you can specify the number of layers, so you can create a different weight matrix for all of these. And then you just basically have a for loop through each of these layers, where you're multiplying the weight matrix, you're adding the bias vector, and you get a new hidden value, and then you get all the way to the end of to something that you can use to make a prediction. So again, with a kind of minimal change, we then are able to implement this new model. So that's it about the concrete examples. Are there any things that people would like me to talk about before I get into the final part? No? Okay. So one thing that I would there's kind of two things that I'd like people to remember going forward, and these are really, really important things, and they're really, really important to think about whenever somebody says good things about neural networks or bad things about neural networks. So the kind of very, very big promise behind neural networks is that neural networks are powerful. They are universal function approximators, and they can calculate any function with some sort of, small conditions about the function being continuous in some way, et cetera. In fact, you can show that particular designs of neural networks can simulate Turing machines. So basically, your whole computer could be replaced with a neural network if you really wanted it to be. And all of NLP could theoretically be solved by taking all the sentences in the world, feeding them into one big feed-forward neural network, and predicting whatever you wanted to predict. So theoretically, NLP is solved, right? Like we don't even need to do this class. These things have the capability of solving all our problems for us. However, realistically, there's a very big condition here, which is that we can learn the parameters of a neural network that's able to do these things from the limited amount of data, training data that we have. So that's the big caveat here. Language is very, very hard and complicated, and the amount of training data that we can come up with is limited. So what we need to do is we need to design our networks or our training algorithms maybe to have an inductive bias, which is another simple way of saying we need to make it easy for them to learn the things that we would like to learn from limited data so they generalize to the things that we want them to generalize over. So anytime somebody hypes the ability of neural networks to do things, think about the second one. Anytime somebody says neural networks are bad, they're not the answer to your problems, think about the first one. Because the reality is more complicated, and this is the reason why things are interesting and why we need to think about things appropriately. So the class plan, I will just go over this very briefly. You can also find it on the schedule, but I've kind of split it up into topics. The first topic is models of words. This includes word representations. How do we calculate representations of words? Also, how do we do training efficiently with the example of word2vec being an example of this? A second example is models of sentences. So this includes more depth into the sentence classification task that I talked about so far. Also, recurrent neural networks and variations of recurrent neural networks. And also, one of the biggest developments of 2018 in neural networks was the very big success of methods to basically learn representations of words in context. So instead of taking a single vector for each word, you instead learn a representation of a word based on its context, and pre-training methods to do this. And people might have heard of Elmo or BERT as specific examples of these. A second topic is implementing debugging and interpreting your neural networks. So one of the unfortunate things about neural networks is that they can be very difficult to debug compared to other methods that we used previously. So this takes quite a bit of know-how. It takes quite a bit of know-how to know where to look when your models aren't working appropriately. And we have about 3 classes, maybe two to three classes that are based on how to make your neural networks train fast, how to figure out when there are problems with your neural networks, and also how can you understand why your neural networks made predictions. And the third topic is something that I think is very interesting recently, and we'll be redesigning the material this year for that. We'll also be talking about sequence-to-sequence models. So sequence-to-sequence models are basically models that take in one sequence and output another sequence. I'll be talking about encoder-decoder models, attention-based models, which are kind of the standard now, and then also a recent development, also from 2017 or 2018, that uses different ways of encoding sentences or decoding sentences based on self-attention, and often goes by the common name transformer models. I think one of the interesting things about a lot of prediction tasks in NLP is that they are structured prediction tasks. So we need to have some good method for modeling the dependencies between the various things in the output. So for example, if we have part-of-speech tags, how do we model the consistency between the part-of-speech tags and the output? Sequence-to-sequence models are one way of doing things, but the research has shown that there are more effective models of doing this as well. And we're going to be talking about things like structured loss functions, like structured perceptron, max margin, optimizing task losses with reinforcement learning, and also conditional random fields, which are good methods for this. Also, we're going to talk about models of tree and graph structures. So one of the very widely known linguistic facts about language is that it's compositional. So you can combine together phrases in like arbitrarily large structures and still get meaningful sentences. And tree-based models and graph-based models are good ways of capturing this. We're also going to talk about advanced learning techniques like models with latent random variables, adversarial networks, semi-supervised and unsupervised learning. Models of knowledge in context. So big neural network models are very, very good at kind of generalizing to new data sets. But one thing they're a little bit less good than some traditional models is memorizing facts, for example. So we have these big knowledge bases of facts about entities or relations or dictionaries or things like this. And methods to incorporate these kind of things into models have been very successful. One still unsolved, in my opinion, problem with neural networks is they have trouble modeling very long documents, both when they want to generate them and when they want to understand them. And I think this is still a very interesting and active research area. And how can we do this? And then finally, I'll be talking about sorry, not finally, but we'll be talking about multitask and multilingual learning, where you can learn from different tasks, like, for example, translation and part-of-speech tagging. Also, how can you learn multilingually across multiple languages? And finally, advanced search techniques for things like structured prediction. So I'll be talking about that in more detail as well. Or maybe Dan will be talking about that in detail. So that's all I have for today. Are there any questions that people would want to ask? As I mentioned, you can always ask on Piazza. Also, I usually hang around after class. I usually finish about 10 minutes early and hang around after class so people can come up and ask questions as well. So if you have individual questions, I'm happy to listen. So, okay, thanks a lot.